So, for everyone's knowledge, we are now live. They should be able to hear you, and hopefully they can hear me. So there was a bit of a delay in getting started with the live stream. So hopefully people who have been waiting on live can now sign in. And I'll introduce the session here today. All right, so just for the two who just joined, if you could sign in on the sheet over there. Okay, so welcome to the CHEM 1200 review session for your final. Would anyone like to remind me what the date of the final is?
Next Wednesday.
Next Wednesday. Awesome. With Professor Kovrak. Awesome. So I have a stack here. These are periodic tables, and they're taken from one of the practice finals online. So this is going to be a big recommendation from me. Should be with you when you're doing practice questions, because you're going to have this with you on the day of the exam. So I'm going to pass around this stack, and anyone who needs one who didn't already print out copies.
These are the whole exam.
Awesome.
Yeah.
So the 4 chapters that we are going to be focusing on today are going to be the ones that are a little bit newer for the final. And then we're also going to include a lot of the more cumulative questions from the whole course. So we're going to start with chapters 7, 10, and 11. And then once that's done, and I'll explain what we're going to do with those, we'll move on to more overall questions, because we're going to need big on those chapters, but then also the whole course, because it's a cumulative final. Okay, so I believe every one of you can do very well in this test, and we're going to make sure that we can answer all of your questions today and set in some good habits for you to do over the weekend and before the final on Wednesday. Okay, so first, I'm just going to introduce the chapters that I want you guys to be thinking about the most for today, and what we're going to hit on in the questions that I have prepared. And then in terms of this review session, the format that I'd like it to take is answering questions, because that is the best way to study, is having questions in front of you and not knowing the answer and figuring it out, because that's what we're going to be doing on Wednesday. All right. So the 3 chapters, bonding and Lewis structures, that's what I call chapter 7 of your textbook. Intermolecular forces, that's going to be chapter 10. And then solutions, chapter 11. So that should have been the last chapter covered in class. Okay, so these are going to be the big ones. And then, as I mentioned on the flyer, but I'm also going to add here, we have some chapter 6, which is electronic structure, like those electron configurations that we're also going to mix in, because that's relatively recent and very relevant. Okay, so much like the test is going to begin, I want to start today with true or false questions. So these are taken from some are from pretty familiar old tests that are on their website, but others I sort of came up with and threw in. And what I'd like to do is to have us answer and then talk about why the answer is what it is. With true or false questions, it can seem really scary when we first see them, because not everything is so black and white. But I think that there's a way to approach this in a way that you can be confident going in that you can get them right. Okay. So I'm going to write the question up here. We're going to say true or false, and then we're going to discuss why. We're going right in. Okay. True or false? The carbon-carbon bond is generally shorter than the carbon-carbon double bond. So we have CC and then C double bond to C.
True.
Okay. Anyone else? Okay, so we have some true, some false, and this is exactly where we want to be because we want to figure out why this is, in fact, false. So, yes, this is false, but why is that, and what can we learn to apply to the questions you're going to get on Wednesday? Bond lengths shorten with strength. So, I want you to imagine two people holding hands and ask yourself is the how strong is their link together. If you see two people and they're holding hands from across the room versus two people that are holding hands really close to each other, the stronger one is probably going to be the one where they're closer together. Okay, so stronger, shorter. It's sort of just an intuitive metaphor for you to think about. Stronger bonds are shorter bonds. Now, which one of these might be stronger? If we have one single bond between carbon and carbon, or two single bonds between carbon and carbon, which makes a double bond. It's going to be this one because there are more shared electrons between those two carbons. So, stronger bond, stronger is shorter. Weaker bond, weaker is longer. Sort of a metaphor with which to think of it. So, they could do the same thing for a compound where there is a nitrogen and then a carbon bond here, and then somewhere else in the compound, there's a carbon with a triple bond to a nitrogen. Let's say this was these were two parts of a molecule for which they gave you the Lewis structure, which we're going to do later. And they asked, how long is this bond versus this bond? This is a single bond. So you want to ask yourself, hello, you here for Chem 1?
Yes.
Awesome, welcome. I'm Aiden. We just started these true or false questions. So why the carbon-carbon single bond is longer than the carbon-carbon double bond? Because between this and this, more bonds is stronger. Stronger just means that it's harder to break. And it's going to be harder to break 3 bonds than it is to break 1 bond. So that's sort of the reasoning we're going to use. So that one would be false. Okay. Any more questions about bond lengths? It's sort of a niche kind of topic. This is one of the few applications I could think of, but definitely anyone who has ideas about that, shout it out. But yeah, that's the thing to know. Stronger bonds, shorter bonds. More bonds is more strong than fewer bonds. Okay. I think I drew this one. Okay. True or false? All molecules in a gas, sample of gas, move with the same speed, which increases with temperature. True or false? Okay. If everyone had to answer, let's just throw out the answer. There's no risk here. no tests here. And I won't judge you for getting it wrong because I got it wrong too when I first saw it. Confusing. Okay, who's for true? Let's raise hands, and I'll describe what the hands are for everyone who's on live stream. Okay, most of the hands in the room are true. Anyone for false? Okay, some hands are false. Okay, yeah. So don't be afraid to answer the question, because our goal is to actually like talk about why this is what it is, which is it's false. It's false. So this is what I call a two-parter, true or false question. There is this statement: the speed increases with temperature of the gas molecules. But then there's this statement, which is all molecules in a gas move at the same speed. So the first one is false, because when you increase the temperature, you increase the average kinetic energy of the sample. And since that kinetic energy is an average, there's going to be some that are a little bit faster, some that are a little bit slower. But they're not all going to be moving at the exact same speed at the exact same time. One intuitive way to understand this, rather than just memorizing, is to think of when you're boiling water. When you're undergoing a phase transition from liquid to gas, it doesn't all turn to gas at the exact same time. Not all of those molecules escape into the gas phase at the exact same time. Which means that some of them have that sufficient energy and some of them don't. But what you're changing with temperature is the average kinetic energy. So that I know is liquid to gas, but the same holds true for gas. If you change the temperature, you change average speed. Okay. So this is a two-parter, particularly hard. And this is true, but this isn't true. So you want to say false for this one. So far that's F and F. Okay, any questions about the kinetic gas theory? Yes.
I just have a question. Does the mass of the molecule play a role in anything, speed or not?
That's a good question. Does anyone have any thoughts about whether the gas of a molecule, the mass of the molecule, changes how fast it moves in a gas? Imagine it's a very good idea. So when we're moving, okay, let's think of why it's called the ideal gas law, because there are certain assumptions that are made when we consider a gas ideal, and we need to pretty much memorize what those are, but also think about them conceptually. So a couple of things that we can ignore about gases: what the identity of the gas is. And the identity is going to include things like its size or any intermolecular forces in that gas. So if I have 1 mole of an ideal gas, it's going to be exactly the same thing as another mole of an ideal gas. And that's sort of like a definitional thing, because if I say ideal, we need to just agree on some ground rules, which is that the identity of the gas is totally negligible. But why is that? So between one oxygen atom and another oxygen atom, or molecule rather, in air, because it's diatomic, there's 2 oxygens. So between 2 oxygen molecules in air, there is just so much distance and so much blank space, essentially, in the grand scheme of things, from liquids to solids to gas, that we don't even consider the fact that it's oxygen. It's going to behave the same way as nitrogen, the same way as methane. And so from that, we could remember that the identity of the gas doesn't matter. Okay, so that's one of the assumptions. And then there are a few others. Another is that the collisions between gas molecules are completely elastic. So there's no transfer of kinetic energy when the 2 gas molecules collide. So this is just another sort of conceptually similar thing to the fact that we don't care what the identity of gas is. if one molecule of gas hits into another molecule of gas, we don't consider that as changing the overall energy of the gas. The only thing that's going to change the overall kinetic energy, average kinetic energy, temperature. So that's going to be what we want to think about in terms of ideal gas. So I would mark down something to study and to memorize is the assumptions of the ideal gas. Okay.
So kinetic energy only depends on temperature, not mass.
In the context of the ideal gas, yeah, exactly. Which is a little bit counterintuitive if you've taken physics, but that is the case with the ideal gas. Okay, so someone commented to write bigger and to write wider, and I'm going to. Yes.
For the true false question, I think about how like the more, the higher the speed, the more. I think I confused it. I thought you said the higher temperature. Because the higher the speed, it higher the average kinetic energy, and you said something about something being different. I think what you meant was it's just that all gases move differently. Like some gases are heavier. Is that what you meant?
So in the context of an ideal gas, the only thing you want to consider in terms of speed is the temperature, because all gases are going to move the same when they are ideal.
So it's like if they said the higher the temperature, it would be different, but they said higher the speed.
I'm not sure what you're asking.
Like had they said, gases move the same and they go up with the higher temperature, then that would be true.
No, that was the question. The wrong part about it was that all molecules in a gas move at the same speed. That's not true. We're talking about average kinetic energy of gas molecules. Okay. And kinetic energy is just, we're going to say that's the same thing as speed. And that depends on temperature. Okay. So those were some gas ones. Why don't we do some of the ones in the 3 chapters that I mentioned? Okay, here's a good one. True or false? I hope this is big enough for people who are on live stream, but I'll write it. Heavier. Yeah, that's a good point. Actually, somebody mentioned in the chat, what does change in a lighter versus a heavier gas is when the molecular weight is higher, the gas effuses slower. Yeah. So a way to conceptually think about this is when you have people moving around in a room, it doesn't matter how large the people are, because their kinetic energy is not going to be dependent on that at all. It's just going to be the temperature of the room, let's say. And let's say people ran faster and bumped into each other, the higher the temperature. However, if I now start opening a very small crack in a door and letting some of the people escape the room, that's analogous to the effusion of gas out of a container. So, as we all know, sometimes it's really hard to slip through a doorway when it's only partially opened. And different people are going to be able to slip through with different rates. Some people are going to have an easier time getting through, moving around, and trying to get out. That is similar to the effusion of gas. So the weight of the gas, which is analogous to its size, is going to change how quickly it will effuse or sort of like spit out of that little hole. So very good point. Thanks so much for mentioning that. Okay, a compound with an odd of electrons will octet rule. True or false? A molecule with an odd, and I'll read it also for people who are on live stream. A molecule with an odd number of electrons will not be able to satisfy the octet rule.
I'll say false.
So true, yeah. Well, true or false? Molecule has an odd number of electrons, and it will not be able to satisfy the octet rule. So what else? Okay. Let's do the hands again, like we did last time. Okay, everyone for true. Everyone for false. Okay. So false would mean that an odd number of electrons will be able to satisfy the octet. Okay. This one is actually true, and I can explain why with an example. So it's very good that you guys responded, because this is how we learn, how we figure it out. So the octet rule says that you need to have 8 electrons in your valence shell in order to be stable. But that really is better illustrated with examples than it is just sort of said. And then there are a couple exceptions that you guys learned in class about times where the octet rule doesn't exactly fit. Okay, so these are going to be times that the octet rule is violated. And one of those times is when the compound has an odd number of electrons. Because electrons can only be in one of 2 places when it comes to any compound. It can either be in a bond, or it can be in a lone pair. And I sort of gave away the answer to this question in saying the lone pair part, because pairs need to be 2 electrons, and if you have 1 extra electron, because it's an odd number, then it's not going to be able to be in a pair, and it's not going to be able to be in a bond. And those are called radicals. So free radical might be like a familiar term to some people. It basically just means a molecule or an atom where there's 1 extra electron hanging around that is not in one of these 2 groups. Not in the lone pair, not in the bond.
So the octet rule is essentially like when, let's just say, like a compound, like with the compound that was shown with the Lewis structure is even. Like there's no, like, let's say for example, it's like, let's say there was 3 electrons. Not 3 electrons, but let's say there was like 3 electrons that were connected to anything, like to H. Then that would not be abiding by the octet rule.
Yeah, exactly. That's a good way to think about it. We have a number that isn't 8 surrounding an atom. There's only a few cases that you have to memorize where that's okay, but then there's a bunch of cases where every other case that it's not okay. So in the case of hydrogen, for example, there are not 8 electrons in this hydrogen's valence shell of electrons. That's okay, because it's hydrogen. It is one of the exceptions where you have fewer than 8 all the time. You'll never see hydrogen with any more electrons than this in the examples that you'll get. But when it comes to something like oxygen, you really do need 8. And then the other exceptions are boron for fewer than 8, beryllium for fewer than 8, and then the ones that are lower down on the periodic table. So everyone, if you have one, grab your periodic table. And I took this from one of the practice tests front pages. So we want to ask ourselves, which atoms is it going to be okay to have more than 8 electrons? So I see carbon, nitrogen, oxygen, and fluorine. And below that, I want to just draw a big line, okay, a horizontal line, and then think everything below that can potentially have more than 8 electrons in its valence shell, because they have d orbitals in which those electrons can sit. But you don't even need to go through the d orbital reasoning every time, because you could just draw that line, no carbon, and below, that's going to be more than 8 electrons. Okay. Okay, so those are two times that we can break the octet rule. We can go low and we can go high. So below 8, above 8. And above 8, it's anything below carbon on the periodic table. A way I like to think about that, you know how we're like carbon-based beings, like humans are made of carbon, that kind of thing. It's like said sometimes, or like oxygen, it's the air that we breathe. Anything below that, when you start getting to these bigger elements that we're a little bit less familiar with, over the octet rule. Sort of a random way to think about it, but this is going to be your friend when it comes to like memorizing for the test. Anything below carbon, you can break the octet rule by going above. Beryllium and boron and hydrogen, you can break the octet rule by going below. Okay, but then there's another example where, sorry, I'm Aiden.
About which it's all about.
Okay, so every atom that you're going to be dealing with will follow the octet rule, except for ones that can take less than 8 electrons or more than 8 electrons. Fewer than 8 electrons are going to be the two Bs, beryllium, boron. Also hydrogen, because it's so small and it's right up there on the corner of the periodic table. But then there's going to be ones that can take more. And this is really best illustrated in examples that I'll get to, which are things like phosphorus, sulfur, chlorine, bromine, krypton, xenon. Those, you're going to be seeing atoms surrounded by way more than 8 electrons, and you're going to also have to say what the geometry of those atoms are. Sorry. Yeah, exactly. So if you just draw that horizontal line at carbon, you'll see that everything below it can have more than 8 electrons. But the funny thing about scandium and all of those metals is that you're not going to see covalent compounds made of only metals. Yeah, I wish I had a better rule for you. It's sort of random. You have to take the periodic table and just chop it up into bits and say, okay, stuff on the right that is below carbon is going to have can have more than 8 electrons in its valence shell. Yes, absolutely. If he finds something where it's scandium or titanium or zirconium, where there's multiple bonds to that atom, like by all means, bigger than the octet rule. But a good rule is just anything below that horizontal. Okay. I wish. I know. If you want to like step out and ask at the front desk, you could ask. Yeah, I'm sorry about the heat. For everyone on live stream, it's kind of hot in here. Okay, so just because we brought up the whole exceeding the octet rule thing, I kind of want to draw a few molecules in which that's the case, and just sort of show why it's okay to have more than 8 electrons in your valence shell sometimes. Okay, so let's do this one. So the question was, compound with an odd number of electrons, can it satisfy the octet rule? The answer is no. And because we're now on the subject of things that will defy the octet rule, we want to show some examples of stuff that goes above. And I also want to do a radical example, because that was sort of the heart of the question. Yeah. Sorry? Yeah, that they won't satisfy the octet rule. Yeah. Okay. So let's do SO4 2 minus. This is ion.
From true or false.
This is just expanding on what I was saying. I just wanted to give an example of a time where we can go beyond the octet rule. Okay. So let's say we have sulfate, SO4 2 minus. So just take your periodic table and say, okay, where is that central atom on the periodic table? S is below that line that we set to draw at things like carbon and oxygen. Anything below that, we can go high and exceed the octet rule. So if this Lewis structure ends up being too many electrons on sulfur or too many bonds to sulfur, that's going to be okay. Okay, so I have S O O. Okay, so the first thing that I like to do when I'm drawing a Lewis structure is to take all of the atoms and connect them with single bonds. So that's going to be step number one.
Hi, I'm sorry to interrupt. I apologize. Unfortunately, I have no control over the climate in the
Okay.
space. They put knobs on the walls that are thermostat, but they don't do anything. They're just kind of ornamental. But I'm sorry if it's a little uncomfortable. All right.
Thank you so much.
Thank you, Rich. And for anyone on Zoom, it's going to be hot in here, but that's okay. It's sort of similar to on test day, right? Turn up the heat. We're nervous, we're sweating, we're trying to answer these true or false questions. Sort of what it's going to be like. Okay, so yeah, SO4 minus. I'm just going to quickly draw the Lewis structure for this, going through the steps that you take when you draw Lewis structures, and realizing first that sulfur is below carbon, below that line that we drew for more than 8 electrons. Okay, so the first thing after drawing all of the atoms and connecting them with single bonds is to count up the electrons. So again, we grab our periodic table. We have sulfur, which is 6, oxygen, which is 6, and there's 4 of them. So it's going to be 4 times 6, and then 2 extra, plus 2 extra, because it's a -2 ion. So totaling all of this is going to be 36, or 32, because it's 6 times 5, and then plus 2. But first, how did I find that there were 6 electrons in oxygen? I counted the tall rows. So I'm looking at the periodic table now. I'm counting the tall rows from the left, and then using that as the number of electrons in the valence shell. So I start at the left. I see hydrogen 1, beryllium 2. Okay, I skip to the other side of the periodic table, to that right side. Right, there's a divot in between, but you skip to the right side. Boron 3, carbon 4, nitrogen 5, oxygen 6. And there's a row there where it's going to be 6 electrons on oxygen, 6 electrons on all of the ones below there. Okay? All right, good luck. And do feel free to watch this back if you can. Okay. Yeah, it's going to be at the same link as this live stream. Okay, so I'm just describing how we're going to get these numbers of electrons. We have sulfur. It's in the same column as oxygen. Oxygen, as I counted from left on the periodic table, I count up using only the tall rows, nothing in the middle. Hydrogen 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and we have all of the electron counts that we need. Plus, you got to remember to look at the charge. If there's a -2 there or a negative whatever, you just add that number of electrons. So our total here, big grand total is 32. Okay, then I go back to my structure and I put sulfur in the middle because that is the only way to have one central atom and then all of the atoms on the outside be the same. As you'll do Lewis structures, you'll get a more intuitive sense for which one goes in the middle, which one goes outside. So sulfur in the middle, 4 oxygen is on the outside, and then 1, 2, 3, 4, 5, 6, 7, 8 are going to be removed from that count. So 32 minus 8, okay? And then we're going to have 24 left. And then we need to populate the rest of this Lewis structure with 24 extra electrons. So you subtract 2 for every bond. So electrons come in pairs, 2 for every bond. Subtract that from the total. Dump 24 electrons now onto the structure. So I'm going to put them in pairs. Okay, so luckily, we had a really neat situation here because each of these oxygens takes 6 electrons, and so we were able to put all of the electrons on just by doing the same thing for every atom. Kind of cool. But we're not 100% done here because it looks like sulfur is totally good with the octet rule, and it actually looks like all these other atoms are satisfied with the octet rule. But our last step whenever drawing Lewis structures is considering the formal charge. Exactly. So as you might have suspected, the formal charge on this is not squeaky clean. So we're going to have to do some work to change the Lewis structure and make the formal charges as fewer as possible. So how many valence electrons are usually on oxygen? Exactly, 6 valence electrons usually on oxygen because I counted across the periodic table. Okay, 6. I see 1, 2, 3. I just see 1, 2, 3, 4, 5, 6, 7 that are currently surrounding it, and I have a -1 formal charge. Let me actually write out the equation of how I calculated for that oxygen a -1 formal charge.
Sorry, where did you get 7? You also counted the single one?
Yeah, exactly. So here's the equation. You do the number valence electrons minus the number of electrons that you see as dots. So these guys think they're right there as dots, so we need to count each one of them individually. So these are all culprits for our formal charge count. They're dots, they're right there, we subtract them. So minus electrons in LP, lone pairs, minus the bonds. So there's another way to do this equation where you do the number of electrons in bonds divided by 2. So for this bond, it's 2 electrons for a bond, and then you divide by 2 for 1. That's kind of complicated. I don't see why you need to do division. Just say 1 bond, you subtract 1. And I like to think of it as like a bond as like a line. And so it's like a 1. Subtract 1, and that's the contribution of this bond to the formal charge. Okay. So we start with 6 on that oxygen. 6 valence electrons for any given oxygen because it is 6th on the periodic table in a row that goes right across. Subtract 6. I see 6 dots surrounding this guy. And then subtract 1. Because we have 1 strike, 1 bond between oxygen and sulfur. Okay, so since all of these oxygens are the same, I'm going to have -1 on every single one of them.
Oh, so when they say like negative, so it's like, I didn't know it was -1 for all of them. I just thought like it was like the whole thing, like you just sort of like.
Well, that's a great point. So the overall charge of the ion is -2, but we can arrive at a net charge of -2 while having more individual charges in the ion. And we'll see how in just a second. So let's look at sulfur now. Let's do the formal charge on sulfur. Let's start with this equation. Formal charge equals number of valence electrons minus number of electrons sitting in lone pairs minus number of bonds. What would that be for this sulfur? I'll draw it big here. Okay.
4 bonds.
Mhm.
Could it be 6 minus 4?
Exactly right. 6 minus 4, and then the formal charge is 2. Plus 2. Plus 2. Okay, so to your point, if we add up all of these charges, we have 0, -1, 2, 3, 4, and then plus 2. Overall, that is -2.
Just so I'm clear, it would be just like if it was all stated out, it would be 6 minus 0, right? Because there's no lone pairs, then minus the 4, right?
Exactly. So
Okay.
for sulfur, I'll write it here. For sulfur, 6 minus 0 minus 4.
And then you get that plus 2. Thank you.
Yeah, exactly. So this is the same overall charge as the ion has. It's minus 2. Great. But we're not 100% done because there's a way to cancel out formal charges. The way that you cancel out formal charges is by forming double bonds. So it might not be totally obvious, and if you get here, you'll probably get partial credit, but we can do better by canceling out some formal charges and forming double bonds. And the reason that we could do that is what we pointed out when we started this problem. It's that sulfur is below that carbon, nitrogen, oxygen line on the periodic table. So it can take more than 8 electrons. Okay, so from here, I take 2 electrons from this oxygen. I put them onto sulfur to make a bond. Every bond has 2 electrons. And then our sulfur now has this bond to oxygen, and I'll draw these electrons big so you can see here. Okay, and then we have this oxygen, and these have the same formal charges as they did before. Okay, what's the formal charge on this oxygen going to be, though? Because here it's a -1, and we have 1 bond and 6 electrons in lone pairs. If I have 2 bonds and 4 electrons in lone pairs, what might the charge be? 6. Let's just use this.
My question is, like, couldn't you still, just take 1 electron from each of them? Because, like, it's not like they have, like, different electrons. It's just that one of them is, like, double bonded.
Yeah, that's a great question. And through the next example, I'll show why you can't just pluck off 1 electron. It would form a radical, which would violate that temporal.
Oh.
Yeah. Okay, yeah. What would be the formal charge on that oxygen using our formal charge equals valence electrons minus lone pair electrons minus bonds? Perfect. Okay, so formal charge here equals 6. That's our big number for oxygen because we found it on the periodic table. Minus 1, 2, 3, 4. Minus strike. That is the difference between getting a little bit of partial credit and getting this question totally right. So this now has no more formal charge, which is sweet. The sulfur has a different formal charge now because you added a bond. Without actually recalculating sulfur's formal charge, why don't we just say what happens to your formal charge when you increase the number of bonds? So you increase the number of bonds by 1 and you don't change anything else. What might happen to your formal charge? Yeah, it decreases by 1, exactly. Because the equation, formal charge equals number of valence electrons minus electrons in lone pairs minus bonds. So we put this up, we bring the formal charge down. Exactly. So this now goes down to +1, and our total charge is still -2, but we've canceled out as many formal charges as we could because we made double bonds. So big picture, something to remember and keep in mind for the test, double bonds cancel formal charges.Use double bonds to cancel formal charges. If everything else seems correct. Okay.
So the reason that you can't just take 1 off of the other one is because the other one changes the formula. So I think I need to, like, understand the first one, because you said that when you take -2 from, like, both oxygen atoms, it still equals -2 overall. Is it a still formal charge?
It's because electrons come in pairs.
Okay.
Yeah, I know that's not like a logical sort of thing, but it. All right, good luck in class. Yes, and you can always watch the live stream. Thanks so much for coming. Okay, so big picture, electrons like to be with each other. They don't like to be alone. If you have a molecule where there is a formal charge, but your electrons are in pairs, we don't want to start plucking off individual electrons if we can avoid it. And we always can. So there's always a way to make our molecule with no single electrons that are sitting without another electron there to be its friend, because they always want to be in pairs. I know that's really somewhat of like a theoretical thing to say, but let's look at this example of a free radical, NO, which you might see on your test. So the Lewis structure for NO, and I know we're getting a little bit off of the true or false here, but this is important. This is one of the cases where you can break the octet rule. Okay. So what's our total electron count for this molecule? I'm doing the first step, which is drawing the atoms and drawing a single bond between the atoms. What might be our electron count?
It would be. I don't think it would be a radical because it's still. Oh no, you would have a radical.
It would be 11.
So, and I'm also going to answer a question that was asked on the chat. So we have 5 for nitrogen, and use your periodic table, find it. 5. Oxygen, 6. Kind of cute how they're right next to each other on the table. So for this one, you just do 5 plus 6 equals 11. Okay, this bond took 2 electrons. 11 minus 2 equals 9. Okay, so a question was, how do we know not to add more double bonds to cancel more charges? That's a great question. In terms of canceling formal charges, you need to sometimes draw the wrong structure before you know what to do next. So in the case of sulfur with 4 oxygens, which is called sulfide, sometimes, and you totally should not panic if you do this on the test, it's part of solving the problem. Sometimes you have to draw the wrong structure to realize that there's a better one out there. If every single one of the atoms on your structure has a formal charge, you might want to experiment. Add a double bond, see what happens. And since sulfur is below carbon on the periodic table, you might end up with a molecule that still is allowed even though it breaks the octet rule. Because that's something that they're going to want to test you on. When you see a sulfur, when you see a phosphorus, when you see a xenon, below the carbon line on the periodic table, more than 8 electrons. So I'm doubtful that you would see something with only 4 bonds that's a sulfur.
So the goal of this, like changing it around, is to get a formal charge of 0 or close to it.
You want to cancel as many formal charges as you can.
So
So the overall formal charge on this is always going to be -2 because it's a -2 ion. But your individual formal charges can be eliminated while maintaining that overall charge. And what we did for that was we made this double bond using one of oxygen's electrons, canceled that charge, and made this +1. So no longer does every single atom in our molecule have formal charge. Yeah, we can't get rid of all of them, unfortunately. Yeah, you
I
know.
was just gonna say, like, so you can't add another double bond to oxygen because what?
That's a great question. So in this situation, our total formal charge -2. The ion that we were given on the test is SO4 2-. That's the ion. Once we get to a charge of -2, while having as few formal charges as possible, we're going to want to stop. But why don't we experiment? Why don't we see what would happen if we added another double bond, snatched another one of oxygen's electrons to cancel out another formal charge? Okay. So now this oxygen and this oxygen have -1 formal charges. This sulfur, let's calculate it. Sulfur has 6 valence electrons, just like oxygen, minus 1, 2, 3, 4, 5, 6. And boom, that's correct. See that? So by canceling out 1 formal charge, we actually didn't even do the whole job. We canceled out more formal charges, and we still have the same overall charge, -2. That's what you're going to want to do. So 6 minus 6 equals 0. Yeah, SO2. SO4, rather.
So is this even better?
That's even better. Sorry. So that is even better. Yes. And it's okay, right? Because usually, do we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons around an atom? Like, no, because it breaks the octet rule. But it's okay here.
It's sulfur.
Yeah, because it's sulfur, exactly. Yeah, sorry for the confusion on that. This should be the right answer for SO4 2 minus. You could also probably Google it and find it. So we might be able to confirm. 4 2 minus structure. Awesome. Okay. So yeah, only 2 of those oxygens. We're going to form double bonds, and then the rest we need to maintain like this because we need that -2 overall charge. Awesome.
So if you kept going, you would ruin it because it wouldn't be -2 anymore. So
Yep.
that's why you stopped.
Yeah, exactly. Plus, this sulfur in the middle, we would be adding bonds to it, and that would start giving it a negative formal charge. So
Oh, okay.
we could actually make another bond to sulfur here. That would give this oxygen a 0 formal charge and this sulfur a -1 formal charge. Thanks so much for coming.
Oh, yeah, because you're adding another one of those ones as you call it, right?
Yeah, exactly. Another one of the ones that's going to be part of our equation. It's going to decrease the formal charge by 1. Overall, this charge would actually be valid. So if we did that structure, you would have -1 here, 0 here. The reason we don't want to do that is because the formal charge should be on the more electronegative atom. So we didn't talk about electronegativity yet, but that's another rule that comes into play when we're deciding which atom to put the formal charge on. The more electronegative atom gets the more electrons. In this case, we're deciding whether to give more electrons to sulfur or oxygen. And I know that my trend for electronegativity is up and to the right on the periodic table. And that's the trend right there, up to the right on the periodic table. So you start from bottom left. Anything that goes right, more electronegative, then anything that goes up is more electronegative. And the most electronegative is fluorine. That's another good way to remember the up and to the right thing. Most electronegative atom, by definition, is fluorine. Cool. Okay, good catch with the SO4 2 minus. That's a great example for them to put on the test. Another one you might see is H2SO4 2 minus, or H2SO4 rather. Neutral. It would be the same thing, except you would have a couple of hydrogens on these oxygens and no overall formal charge at all. Okay, but keep that same principle in mind of making as few formal charges as possible, and you'll eventually arrive at the correct structure. And you might have to try a couple of ones before that happens. But that's sort of part of it. With Lewis structures, you need to sometimes get wrong or weird structures, and then realize the formal charge is wrong, get to the right structure. Okay. How about NO? So overall, there's 11 electrons. -2 for the bond is 9. Now let's just dump the rest of the electrons on and see what happens.
Can I ask a question?
Yes.
So there were a couple elements that you said were that were on the octahedral, and it was boron, valerium, hydrogen, phosphorus, sulfur, and potassium, or kryptonite.
Yeah, that's a good question. I didn't list specific atoms when it comes to exceeding the octet rule because it's really just a line on the periodic table you can draw. So if you look at carbon, nitrogen, oxygen, below that, just draw a big horizontal line. Anything below there can accept more than 8 electrons in its valence shell.
Can you please like write on my paper? Because I'm like, are you talking like in like rows or in like groups?
Horizontal line, so across like that, starting right below carbon. So find carbon, nitrogen, and oxygen. That's one row. Draw a horizontal line that begins right at the base of those letters. And then anything below that is going to be able to take more than 8 electrons in its valence shell.
So carbon, nitrogen, and oxygen, and anything within that group can take is outside of oxygen.
Here, I'll draw this. So okay, so that, yep, anything below that line that I drew right there. Okay, so for people following at home, anything below nitrogen, oxygen on the periodic table has that d orbital to accept more than 8 electrons. Okay,
I have a question.
yes.
I didn't pay attention to it. Where did you get the -2? It was -2.
For SO4,
For, I think it was no.
yeah, so when I'm drawing a Lewis structure, my first step is to draw bonds between all of the atoms. Was that helpful? Okay. So yeah, important to remember that thing with the line. Every bond has 2 electrons, so out of our total count of 11, we subtract 2 to see how many electrons we now need to dump onto the structure to finish the structure. So that's my first step. Always drawing single bonds and then completing by subtracting those single bonds. And now we experiment. So look, 1, 2, 3, 4, 5, 6 on oxygen, and 1, 2, 3 on nitrogen. So nitrogen is not beryllium and boron, and it is not below nitrogen on the periodic table, right? So nitrogen cannot have less than an octet. And right now it has 1, 2, 3, 4, 5 electrons in its valence shell. Not good, not good. So what might we be able to do? And then oxygen, before we get to the octet rule, it also has a formal charge of -1 here. And I could sort of spot that by seeing, knowing oxygen is 6, and then -1 for the bond, and then -6 for all these, boom, 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 boom. -6, that's -1. So oxygen has a formal charge, but even more importantly, nitrogen doesn't have the octet rule yet. So let's put more electrons into nitrogen's valence shell by giving it another bond to oxygen. This solves another problem, which is that it cancels out the formal charge on oxygen. Oxygen now has a formal charge of 0, which is good. Nitrogen doesn't have 8 valence electrons here, which is a problem. But if we do the formal charge, we'll actually find, so if we find nitrogen on the periodic table, it's 5 going across, number 5, right before oxygen, minus 1, 2, 3 lone electrons here, so lone pairs plus that extra electron, minus 2 bonds, which is 0. So as problematic as it is that nitrogen doesn't have an octet here, at least it doesn't have any formal charge. So this is a situation called a free radical. And it goes back to that true or false question we did before, where can you satisfy the octet rule with an odd number of electrons? No. And that is indeed the case here. It doesn't satisfy the octet rule, but it does happen, and it's called a free radical. So that is a Lewis structure to keep in mind, and one that I think you can arrive at if you follow the rules of canceling out formal charges and getting as close as possible to the octet rule when you have an odd number of electrons. When your total number of electrons is an odd number, don't panic, because it might be a radical. And if you end up drawing it and there's still formal charges, then it's not a radical and you made some error in calculating the number of electrons. So always double check when you get an odd number for your total electron count, because we do not want to put radicals where they don't belong.
So for nitrogen and oxygen, it was, I believe, like you said, 5 for nitrogen, 6 for oxygen. That's because they were bonded together. And then once you got the answer, you subtracted it again by 2. After that, there was, I think you said something about the electrons, nitrogen, no, oxygen having something like 0 electrons and that being a good thing. How did you get 0 electrons, and why did you give some of the electrons over to nitrogen?
That's a great question. So for NO, we were drawing the Lewis structure, and we wanted to make a Lewis structure that had the fewest number. Sorry, I'm just trying to find my next problem. The fewest number of formal charges, and also the fewest number of, and also the octet rule for every atom. Right, that's the bedrock of the Lewis structure system. So for NO, the only way that we are able to minimize formal charges and have as many electrons as close to 8 as possible altogether, we needed to make a double bond. So here, right, there were 11 total. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here, we're not satisfying the octet rule, and this nitrogen would have a formal charge. So that's 2 strikes. That's not good. This satisfies the octet rule, but it has a formal charge, so also not perfect. This would have a formal charge of -1, and I did that by calculating formal charge equals number of lone pair electrons minus strikes for bonds. So for here it would be 6 minus 6 minus 1 for oxygen for -1 total.
So it's formal charge minus, what was that second term?
Yeah, I'll just rewrite the equation down here. Formal charge equals number of valence minus lone pair electrons minus bonds. Formal charge equals valence electrons minus lone pair electrons minus bonds. And we're doing individual bonds here rather than doing the number of electrons in bonds divided by 2, which is another way you might see that. Okay, so I had a -1 here, a +1 here, because that's 5 minus 1, 2, 3, 4.
5 minus 1, 2.
Yeah, we'll check out this nitrogen. Nitrogen has 5 valence electrons, minus 3 lone pair electrons that are here, so 1, 2, 3, minus number of bonds, which is 1. So I have 5 minus 3 minus 1. No good, because we have a +1 formal charge. So overall it might be neutral, but we don't want formal charges. So we're going to make a double bond, because double bonds cancel out formal charges. And boom, no more formal charge, and we're as close to that as we're ever going to get with that compound. Okay, I want to do some more problems that are related to, I think it was chapter 10, the intermolecular force one. Yeah.
Just really quick.
Yeah.
So you would prioritize getting a neutral formal charge over satisfying the octet?
If it's an odd number of electrons, yeah,
Okay.
100%.
Okay, so
Because with an odd number of electrons, if you really do count up the number of electrons and it's odd, you have to be thinking they're about to test me on radicals.
Okay.
So one of them is going to have a single electron, and you want to cancel out the formal charge.
So
With that one.
odd number of electrons is going to be a radical.
It has to be, yeah. Because if you think about it, electrons are all only in bonds, which are 2 electrons or pairs, or it's an extra one, which is a radical.
Okay. Thank you so
for
much.
the problem,
Sorry.
it was, okay, so for oxygen, it was 6, 6, 1. For nitrogen, it was 5, 3, 1. But the problem was what exactly?
It was that there was a formal charge on nitrogen and a formal charge on oxygen.
So that's why we
Made a double bond.
So how do you tell? Like what is a formal charge?
A formal charge is just a measure of how many electrons relative to the number of valence electrons are surrounding an atom in a compound.
So electrons relevant to valence electrons.
Yeah, exactly. So you have a number of valence electrons, and then you have a different number of valence electrons in this specific compound. So let's do a let's do another Lewis structure just to illustrate that. H, C, O2, H. Another compound. I'm sorry, this is so small. That says HCO2H. Okay. So I'm going to scatter these atoms, draw them out, and then make single bonds, and then do my electron count just like before. And then we're going to make sure that we cancel out all our formal charges. And hopefully this will help illustrate what that concept is. So we have C. Let's just put an O here. Let's put an O here. And my H's, they seem to be on sort of either side of this equation, right? Because we don't have H2. And so my H's are here. Now, you might be wondering, like, how do we get to this step without knowing? I'm just going to draw the blank form for that. And you just sort of have to play with it. Usually we don't see oxygens bound to other oxygens. Usually we don't see, just hydrogens bound to other hydrogens, because hydrogen can only form one bond. So it's not going to be bound to another hydrogen and then bound to something else in a chain. So if you just use those two rules, this is actually the only possible setup given these atoms. But if you don't get to this, that's totally fine, because you play with it. You put the O's next to each other, or you put the C on the other side of an H, like say I swapped these two. You would find by doing your formal charges that that is wrong. So the reason that we're going to use formal charges is because we need to know what arrangement of the atoms is correct. Because there are many possible arrangements with just two hydrogens, carbon, and two oxygens that it could be. Okay, so I do my single bonds, and then I do my electron count. So I connected 1, 2, 3, 4, 5, 6, 7, 8. So whatever it is, it's going to be minus 8. And now let's tally up how many electrons we start with. So 1, 4, 6, 1, and we have 2 of the 6. So it's going to be 1 for hydrogen plus 4 for carbon. And these are just valence electrons I'm taking from the periodic table, plus 6 times 2 for oxygen, plus 1 for hydrogen. So that's 1, 2, plus 4 is 6, plus 12 is 18. So 18 minus 8 equals 10. Okay, everyone with me on that total count for C, for HCO2H?
Trying to get the I'm confused for I'm confused on some things. Is it like a negative like is there like a positive charge, like 2 charges on this one?
No, this is uncharged.
Okay, so why? Because for oxygen it's 8. You could say.
So oxygen on the periodic table, what I do in order to find the number of valence electrons, I start from the very left, and then I look at the tall parts, and I ignore the valley in the middle. So I'm just showing on my periodic table here what parts we're going to use. So we do 1, 2, this is valence electrons, just to make it clear. 1 hydrogen, 2 beryllium and down, and these are in rows, so 1, 2, and then skip the middle, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine and friends 7, and then all that the right is 8, And the reason these are called the noble gases all the way to the right is because they all satisfy the octet rule without being bounded to anything else.
Okay, so it's hydrogen.
Hydrogen 1,
Well, is 1.
Yeah.
Beryllium is 2. We skip the middle. Then boron is 3. Is it like 3, 4, 5, 6 really?
exactly. So that's why we arrived at 6 for oxygen, 4 for carbon, and 1 for hydrogen. Okay,
So what's the inert gas? There's 0?
well, what's the octet rule?
Oh, that's 8.
So it's a good question. They don't have 0 electrons, or they do have 0 electrons. Just depends on what your frame of reference is. Their outermost shell has 8 electrons, so they have 0 on the next shell. I guess you could say. But the important part is that they have their octet. So like things like xenon, neon, fluorine, helium, those are going to have 8 electrons, except for helium. Only has 2, but it's fine. And you're not going to have to use helium, I don't think. But yeah, helium has 2 electrons and it's one of the noble gases. Okay.
Also, every. Okay, let me just.
You know, I might be able to answer your question a little bit better after this session. I just want to get through this example really quick. But I'm happy to answer your question. So I set out all of my atoms, and I chose this arrangement after a little bit of trial and error with formal charges, etc. Okay? Now I dump the rest of my electrons. I have 10 electrons. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So I decided to just dump these electrons as single electrons onto my more electronegative atoms. And electronegative because I see that they're up and to the right on the periodic table. So I had oxygen, oxygen. These guys are hungry for electrons. They're going to get them. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. But there's 2 problems here. Does anyone see them right off the bat with this structure?
The maximum part for oxygen 6. Oxygen has 6 valence electrons, right? And then isn't it passive?
Yeah, so this oxygen actually does have a full octet.
Oh, it can't.
So it can have a full octet. Yeah, oxygen follows the octet rule because it's above that line that we drew, but it has a formal charge here. That's one of the problems. And what's the other problem? Disaster. Carbon is not below that line. Carbon is us, humans, nature. We follow the octet rule. Above the line, we need 8 electrons around here, and it doesn't have that. So this is totally invalid Lewis structure. Plus, there's this problem that this has a -1 formal charge. I didn't calculate this because we've already seen a couple of times now where oxygen has 1, 2, 3, 4, 5, 6 electrons around it and 1 bond. I know that's a formal charge of -1 now. That's a pattern that you might spot once you start drawing more and more Lewis structures. Okay, so how do I cancel out a formal charge while satisfying the octet rule here? I'm going to make a double bond. Exactly. So that now this oxygen has a formal charge of 0. Awesome. That carbon has 8 electrons in its valence shell. But let's do its formal charge because we're not 100% sure that that's going to be right. Okay. So formal charge, number of valence electron on carbon, 4. Number of lone pair electrons, 0. Number of bonds, strike, 4. 4 minus 0 minus 4 equals 0. Okay. 0 formal charge. Sick. Same thing for this hydrogen, and for this oxygen. I calculated this one in my head, but if you wanted to do it, it would be 6 valence electrons minus 1, 2, 3, 4 lone pairs minus strike. So it's actually the same as this oxygen in that way, right? Because it has those 2 bonds and the 2 lone pairs. Yes.
So I did draw it like that when I was figuring it out, but could this kind of also go into like resonance? So like you put a double bond on the opposite side. Would that count as well? Or no?
Yeah, there are resonance structures here. And have you guys seen resonance structures? Okay. For anyone that was in lecture, were they in lecture? because we can draw a resonance structure here, but I don't want to get into it if it's okay. So really quick, we're going to draw the resonance structure for this molecule, and two things that we want to remember when doing this. So first of all, this is the Lewis structure, okay? We've solved the problem, great. Valid Lewis structure, all of the octets are there. We don't have any formal charges, and the overall charge is 0 because this is a neutral compound. When you got the formula, it didn't have any charges on it, neutral compound. Okay. But what if we rearranged this electron setup and got the same neutral charge out of it? That's actually possible to do, and that's what resonance is. So I'm going to redraw these atoms. The atoms themselves, when you're drawing resonance structures, they stay exactly the same. But the bonds between them and the lone pairs are different. So we have H, C, O, O, H. Okay, so it's sort of like hiding here in the corner. But all of these bonds have to stay the same because all of these atoms are connected in the compound. And they're going to stay connected. It's the same compound. But let's undo what we just did to that carbon. Let's take one of its bonds away here and put the lone pairs of electrons back onto oxygen. So that now has a -1 formal charge. That now has a +1 formal charge because we have 4 minus 3 strikes is +1. Okay, so that carbon now has a +1 formal charge. But there's a bigger problem is that it doesn't satisfy the octet rule. What if we just played around with it, and really with Lewis structures it is playing around and finding what you come up with, and tried to satisfy the octet rule? Your only valid resonance structures are going to be ones that follow the octet rule, period. Okay, so when doing resonance, that's the golden rule. Follow the octet rule, just follow the octet rule. But you can switch around formal charges. So in order to follow the octet rule, I'm going to take one of these lone pairs, turn it into a double bond, which we know cancels out formal charges. Now, the formal charge on this carbon is 1, 2, 3, 4 less. It's now 0. Awesome. Formal charge on this oxygen, though, let's see. 6 valence electrons on oxygen minus 1, 2, 3 bonds and 1, 2 electrons. So -2 for the electrons, -3 for the bonds. +1. Okay. So that could be problematic if we weren't following the octet rule. But realize that if you counted the electrons around these 3 atoms, which are the non-hydrogen ones here, hydrogen is fine because it has 1 bond. It's fine. But these guys, 1, 2, 3, 4, 5, 6, and a bond, -1. 1, 2, 3, 1, 2, +1. Those 2 add up to 0, neutral charge. That's a valid resonance structure. Okay. And yes.
What are the valence electrons? I bet the valence electrons and just like the electrons you got from the, and just the electrons you got from the periodic table itself. Okay.
Oh, that's okay. So what if the number of valence electrons and the electrons on the periodic table are different?
No, like valence electrons are the electrons that you see.
Exactly.
So, okay.
So
then how did you get like 6 for oxygen? Like,
yeah,
6
that's
times.
a confusing concept that we need to sort of clarify because it can get tricky when you're in like a stressful test situation. When we talk about valence electrons on the periodic table, we're talking about the number of electrons that it comes with. So you put an oxygen into a compound, it comes with 6 valence electrons. But once it's in the compound, that's when we talk about the octet rule. So if we just plucked an oxygen out of thin air, it would not follow the octet rule. it would have 6 electrons around it. That would not satisfy the acceptable.
I feel like that's why I'm like when you were adding the electrons together, right? What I'm not understanding is why there's this 8 on the periodic table, like for protons, and how you figure out the electrons, unless it's like an ion or something, you would just it's like the amount of protons equal the amount of electrons. That's why I'm confused why I'm seeing like 6 or 7.
Yeah, like more than that 6 electrons around oxygen.
Like no, like why is it 6 electrons?
Why is it 6 electrons? That's a great question. So the way that we do number of valence electrons is wait, let me rephrase this in a better way. What is a valence electron? It's an electron in the outermost shell. The size of the shell is determined by the principal quantum number n. When n equals 1, you have you have 1s2. 1s2, that's 2 core electrons. When you get up to oxygen, you have 2 core electrons. So the electron configuration for oxygen is 1s, and I wish we could do a better treatment of this, but I'm just going to draw it out. 2s2, 2p4.
Or is it just from?
This is oxygen. Yeah. Okay, so oxygen, it does indeed have 8 electrons. So 8 protons rather, 8 electrons, because it's a neutral atom. But these 2 are different from the other 2 because they are not valence electrons. In order to find the number of valence electrons, we go by the row on the periodic table, not how many electrons overall it has. That's a good point. We're talking about valence electrons. We're talking about bonding. They're the most important electrons in chemistry because they're the ones that are going to move around during reactions.
Okay, so we're talking about. So how do you figure out the valence?
So we start at the left.
Like so, no, it's like okay. I think is it like that thing where one side, like the left side, is S. The middle is, I believe it's no, the middle's not. The middle is F, and then the other side is P, and then the bottom is F. Is that what it is?
So we don't even need to actually think about those blocks when doing valence electron counts. Luckily, it's just the rows. So everything in one parallel row, or a column rather, up and down, is going to have the same number of valence electrons.
Oh, it's the one that you showed me.
Yeah, so it's carbon, silicon, germanium, tin, and lead. Those all have the same number of valence electrons because we go straight down and we say all of these have the same number of valence electrons. For fluorine, chlorine, bromine, and iodine, they all have 7 valence electrons. And that is why we actually group them into one name called halogens, because those electrons determine the reactivity and they make them similar, essentially.
Okay, so. Oh, no.
Okay. So let's talk about intermolecular forces. This is chapter 10. So I'm going to wrap up Lewis structures because we have about 28 minutes to the review session. And we're going to talk about intermolecular forces for a few problems. And also I wanted to touch on molecular geometry because that is, I think, an important and sort of confusing topic. And then if anyone has time after 4 and they want to ask questions, I'll be here. Okay. So I'm going to put up compounds on the board. We're going to say which intermolecular forces apply and talk about why that is. And we're also going to do the molecular geometry for each of the compounds that I put up. Okay. So A is H2S. B is CO2. C is CH3F. Okay. And the question is, we're going to do what intermolecular forces and what molecular geometry. So 1, the forces, 2, the geometry. Maybe we'll do that here. Okay. So I want to briefly touch on the difference between inter and intra. Inter is between two different things. Intra is within the same thing. That got me confused when I was doing this topic, and I just want to clarify that. Yeah, inter, I think like the interstate, that goes between two different states. International, that's across the world between nations. Outside. Intra, inside. It's just the one that isn't inter. Okay, so here we're talking about intermolecular forces. So we have one molecule and another molecule, and there's some force happening between the two. But we need to know what kind of bonds and what shape the molecule is taking in order to know what those forces are. And we can do this in a simple way that goes step by step, and we're going to figure that out now. Okay, so H2S. We want to ask, are the bonds polar, and is the molecule overall symmetrical with the molecular geometry? So number 1, are the bonds polar? So a polar bond is a bond where there are two atoms, and the difference in electronegativity for those two atoms is great. And so they share something that's called a dipole, and that's a polar bond. So we're going to look at the periodic table, have electronegativities, and determine if the difference is big enough. So H2S. I find sulfur on the periodic table. Okay, sulfur all the way to the right and just below oxygen. Then I have hydrogen. It's all the way on the left of the periodic table. So electronegativity trend is up and to the right. So which one is more electronegative, sulfur or hydrogen? That's right. Okay. Okay. And the purpose of, so these are going to be polar bonds because there's a really big difference in electronegativity between hydrogen and sulfur. Physically on the table, they're far apart. So you know that that is an indication. But then quantitatively, we can do difference in electronegativities and figure out if that difference is great enough to be called polar. So if you had electronegativity numbers in front of you, you would need to memorize the range for polar covalent bonds. So for polar covalent bonds, our textbook has it as difference in electronegativity equals 0.4 to 1.8. That's something you just have to memorize if they're giving you electronegativities and asking you to solve. If not, you just need to look at the periodic table and realize they're far apart. One is going to be less electronegative than the other. Below 0.4, nonpolar. Above 1.8 is ionic. Okay, so, but between those two, this is polar covalent bonds. I know it's somewhat weird to have these random numbers, but sometimes in Gen Chem, we do need to memorize random numbers. And a mnemonic I like to use for this, yeah.
What was below 0.4 again?
That is nonpolar.
Thank you.
Yeah, and above 1.8 So I like to think high school, it takes 4 years and you're 18 when you graduate. Okay. H2S, it turns out if you ran the numbers, yeah, the difference is somewhere in this range. I don't know what it is, doesn't really matter, but that means that it's intermolecular forces. We now are going to consider dipole-dipole forces as taking place. Okay, so you have just listing out the intermolecular forces. I'm going to do it verbally because I have all this stuff on the board. Dipole is between molecules that are polar. Ion is between two ions, so something like NaCl. Na is positive, Cl is negative, and the two have ion-ion. Dispersion forces, aka London dispersion forces, or hydrophobic forces, are between molecules that do not have any dipole moment. And it turns out that every molecule, including this one, has a little bit of dispersion going on, even though it is actually a polar molecule. Okay, but what does that actually mean for the strength of the IMFs and for the type of IMFs? For that, once you realize these are polar bonds, right? H to S, the difference in electronegativity is in this range. It's bigger than a non-polar covalent bond. You're going to say dipole-dipole. That's number one. Number two is dispersion. And that's because you always have a little bit of dispersion going on in every molecule, no matter how polar it seems. Okay. Molecular geometry. So molecular geometry, we need to look. Thanks so much for coming. We need to look at two things here: the number of bonds to atoms and the number of lone pairs. So has anyone seen a chart that looks something like? And I'm just showing the class. Yeah, we do have to use the periodic table. I'm not sure what the second part means. Sorry, someone asked about the periodic table in the chat. So this is a chart that has molecular geometries on it. It's something that is in the textbook. It's in chapter 7 for the Lewis structures. So this is something to take a look at, and we're going to understand conceptually why it is. Does anyone not have this chart like on hand right now? Okay, wait, do you have it or? Okay, why don't you pass this around then? Here we go.
It's in chapter 7.
It should be in chapter 7, and if not, you could just Google molecular geometry charts. Okay, thank you so much, commenter. I understand what you were asking. So yeah, he says. So in the chat, I learned that we're not actually going to be using the electronegativity calculations. So thankfully, that 0.4 to 1.8, you don't need to memorize that number, but conceptually understand that in order to have a polar bond, there needs to be this difference in electronegativity, right? Electronegativity trend up and to the right. The left one is going to be a little bit less electronegative, and the right one is going to be more electronegative. That difference causes a polar bond. Okay, so conceptual. This is the number. You don't need to know the number. That's awesome. All right, molecular geometry. So when we have, when it comes to a question about molecular geometry, we need to look at the central atom. Here it is sulfur. And we need to consider, one, how many atoms does it bond to? How many lone pairs does it have? And the way that I like to start answering this question in a more conceptual way is how many atoms is it bound to, and how do those atoms need to change around in order to make the molecule have electrons as far apart from each other as possible. So here it's a sulfur with 2 hydrogens, and that's how many atoms it's bound to. So our central atom, sulfur, 1, 2, 2 atoms that it's bound to. So that's where we start. But there's a few shapes that can actually satisfy that fact, having 2 atoms bound to yourself. But then you have to ask, how many lone pairs of electrons does your central atom have? Here I have 2 lone pairs. On the chart, you'll find that that is the bent geometry, which is basically like one thing in the middle and then two things coming off to the side, and they're sort of like bent like that, like a banana kind of. And that is the molecular geometry for something with two atoms and two lone pairs. Why might that be? Well, these atoms are trying to be as far apart from each other and as far apart from lone pairs as physically possible. So you're going to have a sort of like tripod shape where all of these groups are trying to spread apart as far as possible from each other. So it's sort of like a tripod, like that thing that you put the camera on. And you do have that here. You have a lone pair here, a lone pair here, and a hydrogen here, and a hydrogen here. But rather than a tetrahedron, which this shape would be if these were all atoms, two of those spots are taken up by electrons. So that is what's going to make it just this and just a bent geometry. So think of this as just sort of air where the electrons are sitting, and then the rest is the actual limbs of the person of the Lewis structure that we're drawing. So I'm the central atom, these are my hydrogens, and I'm being squished down by the electrons. Okay, that's how I think about it. That's also the water Lewis structure and the water geometry bent. Good to know. Okay, so we figured out that those are polar bonds, dipole, and dispersion. Another thing, in this molecular geometry, if you have these two different types of atoms, you're going to have an overall dipole moment that does not cancel out. So it's another layer. Once you discover that it's polar bonds, once you've discovered the molecular geometry, you now have to ask, is it symmetrical? This, luckily, is not, well, for our purposes, it is not symmetrical because of that tripod that I drew before. We have two electrons here that are on this side, and then the sulfur with the two hydrogens on this side. Here, I can draw these dipole moment arrows, and they make an overall dipole moment, like a pizza slice, that goes towards that sulfur. Okay, so there's an overall dipole, it is not symmetrical, and it is polar. Let's do the example of CO2. So, first things first, IMFs. Is it polar? So we take out our periodic table, we see the carbon and oxygen. Now, since oxygen is so electronegative, the bond between carbon and oxygen is, in fact, polar. It's a polar bond. That's because oxygen is one of the most electronegative atoms. Carbon is two atoms away. That's not a hard and fast rule, but there's enough distance between them that you have one that's less, one that's more. If it was something like nitrogen and oxygen, that would no longer be polar because they're right next to each other on the periodic table. So use your periodic trend, see that there's difference in the placement on the table. That is polar. Okay. So we're going to have dipole here. Or are we? So definitely dispersion, right? Because every molecule has dispersion. But are we going to have dipole? So let's look at the overall molecule's shape here. We have a carbon and two oxygens. But how many lone pairs do we have? When we draw out the Lewis structure, so the Lewis structure for CO2, I mean, that's a problem of its own. But let's say you drew it out, or let's say you were even given it, you would be able to know that it is this. So check it out. You have carbon, and then two oxygens. And there's no lone pairs on this carbon. Turns out that's actually a straight line, and it's linear. So on that chart, if you check out the thing with two bonds, no lone pairs, it's going to be linear. So it would be like that central atom in the middle, two atoms on either side, linear. Simplest molecular geometry. And what happens here is that the dipole moment between that carbon and that oxygen is exactly the same in two directions, and so it cancels out. So physically, if these are my oxygens, they're both pulling on me in the same exact way. There's no overall difference in electronegativity because one's going that way, one's going the other way, and we're still. So nonpolar overall. Here I'm only going to have dispersion forces. If I did have dipole forces, we would need an overall dipole moment. Yes.
What exactly is dispersion? When you write that, what does that mean?
So dispersion is basically the electrons in an electron cloud bouncing around and collecting on one side and collecting on the other side at sort of random times. So in the electron chapter, we went through electron density being a sort of probability density. But if this is true and we don't know exactly where electrons are, then they sometimes tend to one side or sometimes tend to the other side, sort of randomly.
That's chapter 10.
That would be chapter 6, the electron structure. Yeah. But you don't even really need to get that deep to know, to gain an understanding of dispersion, because think of it as something dispersing. If you poured a bunch of rice into a bowl and shook it up, some rice would collect on one side of the bowl and some other side of the bowl would have less rice at any given time in that shaking up, because the movement of those are random and they're going to stay in the bowl, which is like analogous to the orbital, so the probability density. We don't know, like, is all the rice going to be on this side? Is all the rice going to be on that side? So when something has a cloud of electrons and they do collect on one side, that side gains an extra negative charge, and then since it doesn't have as much electron density, that side gains that charge, positive charge.
Thank you.
Yeah, so that's dispersion. It's always happening everywhere, but sometimes we have a set dipole, like in the case of H2S. In CO2, even though you have dipoles, they cancel each other out because you're in a linear structure, and these two atoms are exactly the same. So you have your Lewis structure down, you'll know how to draw these, and then you'll be able to say that's linear, and it cancels out because it's symmetrical. Okay, CH3F is the bond between carbon and hydrogen polar, and is the bond between carbon and fluorine polar. So I'm going to draw out this one for you. And now let's figure out if between carbon and fluorine there's enough of a difference in electronegativity to make it polar. So we're not using numbers, but we are using the periodic table. Are these guys directly adjacent to each other on the table? Like, are they connected? No. So there's going to be enough of a difference of electronegativity here for me to say between carbon and hydrogen, that's a dipole. That doesn't mean that the overall molecule is polar, because we need to consider a situation like this where they might cancel out. They might just be spreading in all the same direction. But here, I only have one fluorine, and I have 3 hydrogens. So while these guys are down here in the tripod shape, this guy is up here, and there's an overall dipole that faces up. Okay, so not only are the bonds polar, that was our first step, but 2, there's an overall dipole because those individual ones don't cancel out. Okay, so 1 is going to be dipole-dipole. 2 is going to be dispersion. Okay, so let's do a different scenario using similar atoms to illustrate why you can't always assume dipole-dipole when you have polar bonds. So what if we had CH, let's do CF4. because we want polar bonds. Okay, so carbon with 4 fluorines. The central atom is going to be one thing, carbon. The surrounding atoms are also going to be the same thing, fluorine. So in this case, if we have 1, 2, 3, 4 surrounding that central atom, they're all going to be pulling on carbon with the same strength in all of the opposite directions because we want our bonds to be as far away from each other as possible. So while each of these bonds certainly is polar, overall it's nonpolar, and that's what determines the intermolecular forces. So here with CF4, the only one we're going to have is dispersion because there is no overall dipole. Okay. And let me just throw down another example because I want to show this type of intermolecular force. If we had HF, number one, this is a polar bond between H and F because if you look all the way at the left of the periodic table, there's hydrogen. If you look all the way to the right, that's where fluorine is. They're very far apart, difference in electronegativity. Cool. 2, this is not a symmetrical structure because on one side you have H, the other side you have F. There's nothing balancing out here. It's a dipole that points directly towards the fluorine. But there's another thing that happens with nitrogen, oxygen, and fluorine when they are bounded to hydrogen, which is hydrogen bonding, quote unquote hydrogen bonding, because it's not actually a covalent bond, but it is a type of intermolecular force. So we're going to have 1 dipole-dipole. 2 dispersion. But 3 H bonding. And you need to memorize N, O, and F. Those are your hydrogen bonders and nothing else. So if you're given something like HI or HBr or HC, no hydrogen bonds. But whatever you want to do to memorize NOF for hydrogen bonding, these are the only ones that can do it. Nitrogen, oxygen, and fluorine. You could say they're fond of hydrogen bonds, FON, something like that. Okay.
Those
Hydrogen
three only
bonding.
make hydrogen.
Those 3 are the only ones that can make hydrogen bonds. So I'll give another example of a compound that does this. So H2S, polar, asymmetrical. What about NH3? This is a nitrogen with 3 hydrogens. So we want to know the intermolecular forces here. And we realize, number 1, polar bonds. So hydrogen is pretty far away from nitrogen on the periodic table, polar bond. There's enough of that distance there. But the way that I really know that that's a polar bond is because I already memorized the part about hydrogen bonding, NOF. And in order to have hydrogen bonding, you have a bond that is so polar that it exposes this positive charge on the hydrogen and causes this other kind of intermolecular force. It could help to sort of conceptualize it that way. I don't think you would have to memorize that deep of a level other than just NOF to hydrogen bonding. And the reason is that sometimes this nitrogen steals a lot of hydrogen's electron density because it's a probability density, sort of like dispersion. You know how it's like the rice bowl shaking around? Well, imagine that one side of that rice bowl had a magnet on it, and it was magnetic rice, and so a lot of the rice tended to that one side. That's what nitrogen is doing to hydrogen right there. So that's hydrogen bonding, because then you have another nitrogen over here with its 3 hydrogens that's saying like, wow, that looks like a really nice partially positive hydrogen. I'm going to make a hydrogen bond to that with my lone pair of electrons. So nitrogen, oxygen, and fluorine, they'll all be doing this. And this is such a tight intermolecular force that it causes those compounds to be much stronger and more tightly bound than something that doesn't have hydrogen bonding, like CH3F. I'd wager that this is a gas because it doesn't have strong enough intermolecular forces. Right. And one more example, just to close, let's do the Lewis structure for NO2.
And excuse me, before you erase that, would the intermolecular forces for NH3 be the dipole-dipole dispersion and H bonding, or be all 3 as well?
All 3,
Okay,
precisely. Yeah.
thank you.
Yeah, thanks for catching that. So it's the same actually as HF.
All right.
So I know we didn't touch on chapter 11 at all, but that's a lot of math, and I hope that you can use those equations and solve problems. It would be even longer if we were doing math here. So for the sake of efficiency, we're skipping chapter 12, or 11 rather, NO2. Okay. How many valence electrons does nitrogen bring? 5. How many valence electrons does oxygen bring? 6. 5 plus 6 times 2 equals 17. Okay, now I put out my atoms. I need them to be all that's way too tight. Don't be afraid to take up space. N-O and O. Bond, bond, because I want all my atoms together. That's something I do whenever I'm drawing any Lewis structure. Okay, 17 minus 4 equals 13. Wait a second. That is an odd number of electrons. Okay. 5 plus... Okay, there must be a rhyme or reason to this, so we're going to figure it out. Yeah, NO2. So we took 4 electrons to make these 2 bonds. We have 13 electrons left. Let's dump them on our atoms and see what happens. So I'm going to start with the more electronegative ones, which are the oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 12, and I have 1 more. That's 13. And sorry. This is the reason why I had 13 electrons. I knew I was missing something. It's NO2 minus nitrate minus 1 charge. Okay, so we had plus 1 extra electron. Yeah, sorry about that. As soon as you see that you have an odd number of electrons, you have to say that something is fishy. So probably a good example that we saw what that looks like today. Go back, double check. If there's a negative charge, don't be like me. Add in that extra electron to make it even. You definitely want an even number of electrons. Okay, so now I have 2 electrons that I dump onto the nitrogen. So here, there are 2 problems. Number 1, this oxygen, if you do 6 minus 6 minus 1, it has a negative 1 formal charge. That's not great, but it's okay because oxygen has an octet. But this nitrogen, if you do 5 minus how many lone pair electrons?
Good day.
Take care. Thank you for coming.
It would be 2 and then another 2 for the pairs.
Yeah. So, first of all, there's a plus 1 formal charge here. But there's a bigger issue. How many electrons are surrounding nitrogen? 1, 2, 3, 4, 5, 6. Head flies off. Octet rule broken. Totally not cool. We can't have that. So to cancel out the formal charge and restore us to the octet rule, I'm going to make a double bond. So canceling out formal charges, we're making double bonds. All right, now oxygen, if I added, I took away one electron, or no, I took away 2 electrons and I added 1 bond. So this would be -4 minus 2 equals 0. Now oxygen is happy, it has a 0 formal charge. Awesome. But this nitrogen still has a, oh no, it also has a 0 formal charge. So overall it has a -1 formal charge, which is exactly what NO2 should have. One more thing you can do here, just to be extra good if he asks for resonance structures, is that realize that this could easily be the same, but just the mirror image. So you could do nitrogen with 1 bond to oxygen on this side and 2 bonds to oxygen on this side. It is literally the same exact thing.
It's just mirror, right?
Yeah. So technically you could say that's a resonance structure because these two, this oxygen is a different oxygen than this oxygen, and the electrons can bounce between the two.
If you don't mind, what exactly is a resonance structure? Like, how would you define it?
It's another way of drawing the same molecule with a different arrangement of electrons. So same molecule, different arrangement of electrons. That's the definition of resonance structure. So that's that's the definition. But more on actually answering questions, you would want to realize that you can make the same molecule while still maintaining the octet rule. That's the foundation of doing resonance structures, is maintaining the octet rule. The double bonds and each oxygen.
You said same molecule, different structure, right?
Yeah.
Thank you.
And in terms of the same, of putting the double bonds in each oxygen, you can't do that because you would have too many electrons on one of the oxygens. Do you have a
What time do you
reset?
finish? Yeah, I gotta.
I'm finished right now.
You're done?
Okay.
All right, I finish up. I'm here until 5, so when you're on your way out.
All right. Do you guys have any burning questions I might be able to answer on the board while we still have? Okay.
I'm just trying to absorb whatever you're teaching.
Is there a certain way the free electrons should be organized, or is it just however? Like,
The free electrons?
yeah. If you see for M, can those two on the top and on the bottom would be a problem? Or it would.
This is the Lewis structure, and then that's a resonance structure below it.
What I'm asking
So,
is,
yeah.
If the N, right, it has the 2 free electrons.
Mhm.
If you place it like right
Oh
under
yeah,
it,
that's no difference. Yeah. You just want to look at what's surrounding the atom. You could draw it like this, if you want, but we like to go top down for some reason. I don't know. It's all the same. And also we like to make it, rather than this, we like to have this. My opinion on why that is, it's prettier. It looks better. There's no scientific reason for that. But these are the 2 structures you would draw. You can't do this because look at that oxygen. That's above the octet rule. Oxygen is the dividing line along with carbon and nitrogen, and it doesn't have the d orbitals to support any more electrons. So I'm going to make sure that nitrogen keeps its lone pair. Okay. Thank you everyone on YouTube for coming. I'm going to stop the stream now and answer some more in-person questions if anyone has it. But the oxygen would have only 4. So this would have only 4. Here the oxygen has 6 electrons in lone pairs and 2 electrons in this bond. Here, the oxygen has 1, 2, 3, 4 electrons in lone pairs and 2 bonds, each of which has 2 electrons. So that's a total of 8. So it does have 8 in both cases. I'm not sure if that explained the question, but try to play around with the Lewis structures. If you put something together and you see that it breaks the octet rule, then here's yeah, so something like that. Yeah, so just realize nitrogen can't exceed the octet rule either. If we have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10 on nitrogen, we're out of luck. Okay, so yeah, go back to your total electron count. You got to have all the electrons there. If dumping them all there and making too many bonds exceeds the octet rule, that can't be. But yeah, don't panic too much about the. So glad you found it helpful. The chat was saying that it was helpful to have the chat. Yeah, thank you everyone again that was on live stream. Really appreciate it, and feel free to watch it back. Hope it's helpful, and good luck on your final. You all do great.